Welcome everyone. Today's talk is a combinatorial approach to categorical Möbius inversion and magnitude by Juan Pablo Vigneaux. Take it away.
Hi. Well, thank you. Thank you for the invitation. It's like a privilege to have the chance to, I don't know, explain this work that I've been doing for the last, I don't know, a year or a year and a half. Still, I wanted to have it in archive before this presentation, but I failed with that. But it's going to be there soon, hopefully by the end of this week. So the subject is around magnitude, which I think is something that has attracted maybe increasing attention among people that are interested both in topology and category theory, or maybe geometry in more general, and category theory, because of some very rich connections with, on one side, metric geometry, and on the other side, homology. So there is a magnitude homology. And what I want to, well, I will explain a bit what's magnitude and how it's defined. So it's defined through this process of Möbius inversion, or it can be defined that way. And we'll try to find a combinatorial perspective to look at this. So the outline of the presentation is the following. First, I want to motivate and explain what is the traditional definition of magnitude. So magnitude as it was defined by Leinster, but also motivated by Rota's work, combinatorics, and maybe some small like reformulation of the definition that I introduced with one of my students, but also it was introduced independently by these people in Turkey last year. So yeah, that's maybe a first result that I wanted to present. And then that will also motivate, I think, this more general question for a combinatorial interpretation of the Möbius inversion, I hope. So that in the second section of the presentation, I want to explain what is this combinatorial interpretation and how you can recover from it what was known already in some particular cases. And well, after that, I would like to apply that idea to get like a new formula for the magnitude of metric spaces. And maybe that direction could have this rich, or at least in that direction, it could be a bit more straightforward to establish these connections with magnitude homology or with analysis also. And at the end, I want to offer some perspectives to problems that I'm still working on, and maybe some people here will be interested in working on those problems too, I hope. So yeah, so that's the plan for the talk. So concerning the definition of magnitude, in certain sense, so in a very precise sense, it can be traced back to certain work made by Rota in the 60s. So he wrote a series of like foundational papers. He called the like theoretical papers in combinatorics, and one of these was about this process of Möbius inversion. So Möbius inversion initially is something for integers, like integers organized in a poset of with relations of divisibility. So that's what Möbius did in the 19th century. But then Rota realized that indeed this corresponded to a general procedure. You could get any poset, and then introduce this matrix, okay, which has a value 1 if A is smaller or equal than B, and it's indexed by the objects of the poset, and it's 1 if A is smaller or equal than B, and 0 otherwise. And in fact, this is like a little proposition. This set of matrix is invertible. And this inverse is called the Möbius function of the poset. And you can define the magnitude as the sum of the elements of the inverse. Now, in fact, this is called Euler characteristic in Rota's work. And the reason is the following. That because there is a theorem that he attributed to Philip Howe, that if you have a poset, then when you look at this inverse matrix, the component AB of the inverse matrix corresponds to an alternating sum of the number of non-degenerate paths of length k that go from A to B. So a path of length k is something of this form. Here you have A, here you have B, and you can put a k minus 1 objects in between, where not any two successive things are indeed different. So if you want, all these inequalities are indeed strict. But okay, I wrote it this way because in the categorical general case, here you can suppose that there are a lot of arrows later, and it's just the only requirement is that the arrows are not identical. So it follows that this magnitude equals like the topological Euler characteristic of the classifying space of P. At least when this exists. Now, so for example, if P is finite, or there has to be some convergence condition. That is something that I'm going to mention later. So yeah, there is this kind of rich, and also that this is also why this function is important in combinatorials. So it's important because you can identify this number as an alternating sum of some objects, and in the applications that Rota consider, these k paths also have some interpretation in themselves. So it's something that you would like to count. Now, much later, like in 2008, published in 2008, maybe a bit before, Leinster realized that you could generalize this to any finite category. Okay. The poset doesn't really have to be finite. It just have to be locally finite. When you go to general categories, it gets a bit tricky. But for finite, at least, it's very clear how to do it. So you introduce again a matrix. Now the matrix is indexed by the objects of the category. And instead of just taking values 0 or 1, it takes values like the number of homomorphisms between A and B, which we're supposing is a finite number. Indeed, this definition is very general because you can also take A to be an enriched category. So in that case, the of AB for any AB is going to be an element of some category that has a monoidal product, etc. And then this could be one other way. This could be some other way of measuring the size of an object in B. So yeah, indeed, this is like also something that can be generalized to enriched categories. But if you don't want to think about enriched categories, you could simply think that this is the cardinality of the homomorphism set. And of course, you recover the poset case because in the poset case, you can encode it as a category where like each inequality becomes just a single arrow. And the definition that Leinster introduced is like you have a weighting and a co-weighting. So a weighting is a vector that you can multiply, that you can use to multiply zeta on the right, and that gives you a vector of ones. And a co-weighting, if you want, is a weighting of the transpose of zeta. And what Leinster shows is like when A has a weighting and a co-weighting, then in fact the total weight or the total co-weight are the same, and this common value is the magnitude, or is what he defined as the magnitude. So only in those cases for him there is a magnitude. And you recover indeed the poset case because when zeta is invertible, indeed there is just one weighting, and you can find it from the inverse. So it's the only weighting is the row-wise sum of components of zeta, and the only co-weighting is like the column-wise sum of components of zeta. So you recover also Rota's definition. Now, Leinster had already also a combinatorial interpretation for what this inversion had to be, but not in general. only in the like kind of very restricting hypothesis. And the very restricting hypothesis, like A has to be finite, had to be skeletal, and also satisfy this condition that the only idempotents are identities. So the conclusions indeed of like the fact of assuming all that at the same time is that every time that you have a cycle in the category, so a sequence of morphisms that come back to the same object, this cycle indeed has to be composed purely of isomorphisms, but also because the category is skeletal, it can only indeed, the only possible cycle is just the identity. So there are no like non-trivial cycles in the category. And yeah, you're going to see briefly that this is indeed very important, but when A has Möbius, so he proved that under these conditions, A has Möbius inversion, and there is this explicit formula for what the inverse should be. So it's a sum over paths, pretty much as in Hall's theorem. It's also alternating, but now there is this additional factor that you have to add. You have to normalize by the kind of automorphism group of the path, if you want. So the path visits the objects C0, C1 up to CK, and then you have to divide by the cardinality of this automorphism. I mean, all these endomorphisms turn out to be automorphisms, and you have to normalize by that. And the proof that he proposes is just by direct verification. So there's the formula, and then you verify that is the inverse of theta. So it's not a particularly general proof. So I will present another proof of this later as a particular case of what I want to introduce. Then I wanted to mention that briefly, I'd say that we have a more general definition, a slightly more general definition of magnitude. Yeah, so this is what Akaya and Nulo introduced last year, and in parallel us, we didn't know about each other's work. So it's somehow a simple idea is that you take zeta, and when it's not invertible, instead you take the pseudo inverse. So there is a unique, for any matrix with complex coefficients, there is a unique Möbius pseudo inverse. Which is the only matrix that satisfies these four equations. So you can take that as if you want your pseudo Möbius inversion, and now you can prove, if you want, that whenever A has magnitude in the sense of Leinster, then you can compute the magnitude as the sum of the components of the pseudo inverse. But this definition indeed is more general, because now we don't need to suppose that a matrix has a weighting and a co-weighting. So indeed it works for any matrix, because there is always a more parallel pseudo inverse. So it's a slight extension of the definition. Akaya and Undu also proved that it's invariant under equivalence of categories, which is what you would like to have, in fact. And what we showed is that indeed it's nice, because then you can see that many properties of the magnitude sort of follow from properties of matrices. And I think this could be exploited in a way more kind of a powerful way at some point. For example, when you consider the product category, so the product category has the objects are like, yeah, you have to multiply the object sets, and also for every pair of objects, the morphisms also correspond to the product. Now, so a morphism is given by a pair. Now, that means that the zeta function is the canonical product of the zeta function of A and the zeta function of B, okay, which just means that you have this equality. And this is nice. So the Moore-Penrose pseudo inversion commutes with the canonical product. So that if, well, here there should be a plus. So if you compute the pseudo inverse of this matrix, is the pseudo inverse of this one, a canonical product, the pseudo inverse of this one. So that from this, it follows kind of directly with this formula that I just presented, that the magnitude of A times B is the magnitude of A times the magnitude of B. Yeah, and we proved other things like that, and I think maybe this could be exploited further. Okay. So yeah, so that's the end of the section 1. I don't know if there is a question so far or something. Yeah. There is something in the comment. Ah, yeah, it's just me.
No question.
No, now I don't know how to close. Okay, yeah, no. Good. So now about the combinatorial interpretations of this Möbius inversion. Okay, so sometimes I will denote this mu. Okay, so mu is zeta minus 1. So in fact, what appears already in Rota's work and also is very exploited in the theory of magnitude is that at least formally you could expand a zeta to the inverse of zeta as a power series, where here you have a minus 1 power k, and then this is zeta minus the identity matrix to the power k. Huh? Now, this zeta minus the identity, let's say you have a poset. You can interpret it as the adjacency matrix of a directed graph, because vertex set is the objects of A and has edges just when there are like strict inequalities. Now, because precisely when you subtract the identity, you remove the self loops. And then Hall's theorem follows from this expansion, okay? Because precisely if you have a finite poset, this is going to be a finite sum. And when you specialize this to like, I don't know, AB, what this is going to be counting is the number of K paths between A and B. But more generally, this formula 3 is at the root of what's called like magnitude homology. So where there is a pretty much, if you want, one way of generalizing like Hall's theorem. But when you do this, yeah, for a general category, you cannot avoid the fact that this sum can be infinite, okay? Because in a poset, somehow everything is like kind of unidirectional. So you have a finite poset, well, at most you can have a path that is of the length, the height of the poset. But if you have a category, well, now you can come back. Things are not unidirectional anymore. So even if you have a finite category, you can have infinite paths within the category. So you cannot a priori bound this sum. It's a series. And it could be that it's a divergent series. Okay, so when you can have something like Hall's theorem, which is this identification of the magnitude with an alternating sum of, like, if you want an alternating sum of Betti numbers in magnitude homology, you have to suppose there is something like a component-wise absolute convergence to actually have the theorem. So the motivation a bit for what I'm going to present is like to maybe obtain a different representation where you have finite sums. Okay, but of course there's a price to pay, so we're gonna see. But now there is also this one that I already mentioned. And this one indeed is not proved using this expansion, but rather by this direct verification. So those are the two approaches that I would say are present in the literature. Now, this new approach that I would like to propose is the following. So we are going to suppose, at least from the beginning, that zeta is invertible. Indeed, I want to go beyond this because precisely we introduced this pseudo-Möbius inversion, Möbius pseudo-inversion. And in principle, the question that I have, and it's partly answered, is like, what is the combinatorial meaning of that? You know, like, but if you want to answer that, well, at the beginning, you have to have what is the combinatorial meaning of the Möbius inversion in general? Because we only have the meaning in this kind of very restrictive setting that I already showed. So yeah, I will focus on that for the beginning. So we suppose that zeta is invertible, and we would like to find a combinatorial interpretation for the coefficients in any case without making any assumption of the category. So the starting point is this, I call it like Cramer's formula now, that when you have the inverse and you want to compute the component ij, what you can do is to, well, basically here you have the cofactors and then here you have the determinant. So you can say like you know this. So this is the determinant of the matrix zeta when you remove the row I and you remove the column j. So that's the meaning of the little apostrophe at the end. Yeah, so here you remove row I and you remove column j. There is a sign, and then here you quotient by the determinant. So the combinatorial interpretation follows from a combinatorial interpretation of the determinant. So if you know that, then you have an answer because you can apply this to this part and to this part. Although the answer turns out to be slightly different. And now I realize here that I introduced another typo. Here, yeah, this will be confusing because it's not compatible with the notation later. But you're going to have a sum over a certain kind of objects that I'm going to call connections. And in the denominator, you're going to have a sum over another kind of object that I call linear subdigraphs. So yeah, this quotient should be inverted. So why? Well, let's start with what happens with the determinant, okay? So there is something that indeed is called combinatorial linear algebra. And it has like some, I don't know, maybe can be traced back to the 1920s or something by, was it first, I think, first introduced by Coates, which is this idea that, okay, maybe you can see when you take the determinant and you expand it as a sum over permutations, you can see each term in that sum as weights over certain collections of paths in an associated graph. Okay, so here you have a category A. Okay, we could suppose that it's enriched. Okay, here the only thing that we care about, in fact, is the zeta matrix. Okay, so we have a zeta matrix of A times of A to let's say the real numbers. So yeah, this could come from an enrichment, or it could just be a simple category. And now you introduce a graph dA. Okay, it's a directed graph, also weighted. The objects, the vertices of the graph are the objects of A, and you put an edge from A to B with weight zeta AB every time that this zeta is different from 0. And now what you would like to call a linear subdigraph is a subdigraph of this dA made of cycles. So all these cycles are supposed to be vertex disjoint. So you can imagine that if you have a permutation of the objects of A, you could see that each permutation induces a cycle decomposition of dA. So it induces a linear subdigraph. So if you want, this is some kind of rewriting of this expansion of the determinant in terms of permutations. But now you see each one of these permutations as something more geometrical or combinatorial in nature, as these joint cycles in an associated graph. Okay. So yeah, this is the formula that is presented here. So the determinant of zeta is this sum over linear subdigraphs. Now, what we're going to associate to a weight of a linear subdigraph is the multiplication of the corresponding zeta values for all the arrows that are indeed included in this cycle, the collection of cycles. And what we are going to call the sign of a linear subdigraph is this -1 to the power n, which is the number of objects, plus CL, where this is the number of cycles. I think I can show you an example. I'll skip a bit. So for example, here we have this zeta matrix. Okay, so it's 2, 3, 1, 2, 2, 0, 0, 1. So this you could represent as a graph of this sort. So this could be the graph, let's say dA. So where here there is, for example, an arrow from 1 to 2 with weight 3 because there is a 3 here. Now I'm saying the determinant is -2, and because of what I presented, the determinant, you can compute it as a sum over like linear subdigraphs. So these linear subdigraphs are disjoint collections of cycles. So for example, here, what could be a disjoint collection of cycles? Well, you have the one that is 1, 1, 1. So this is a disjoint collection of cycles, and its weight is the multiplication of all the associated weights. So this disjoint collection of cycles has weight 8. And has sign. So the sign is -1 to the power the number of objects, which is 3, and the number of cycles, which is 3. So it has sign +1.
So I think you might have done a error here. Like, isn't the lowest cycle having weight 1?
Ah,
So I think
sorry,
it should
sorry.
be
Yeah,
2
yeah,
times
yeah,
2
yeah.
times
No,
1,
no,
so
no,
then
yeah,
you get 4.
sorry. Thank you, because this is I could have yeah. So it should be 4. Yeah. Yeah, and then you have this other possible cycle, which is here and here, like 3, 2, and then 1. So this one has 6, weight 6, no? And sign -1. Yeah, and that's how I'm going to get the -2. So save the day. Yeah, so this we said is 4 with sign +1, and this is 6 with sign -1, because precisely they differ, the number of cycles differs by 1. So the sign changes. And when you sum these two, these are the only two, and when you sum, you get -2. Okay, so we have that thing, and now for the inverse, it's a bit different. I mean, you use the same idea, but now because you're removing the row I and the column J, the vertices I and J in the graph are going to play slightly different roles. So now there's only going to be an arrow exiting from I, but no arrow coming to I. And there's only going to be an arrow entering J, but not arrow in the other direction. So that translates into the fact that indeed you get a path from, let's say, A to B or I to J. And then in the complement of that path, so in terms of like all the other vertices, they get a linear subgraph. So there is a linear subgraph of the complement of the path and then a path. And this is what it's called a connection. So yeah, because A has out degree 1, B has in degree 1, and the other vertices are balanced. So all degrees are 1. Of course, there is kind of a different case when A equals B. In that case, you don't have anything on A. There is no cycle, no self cycle there, and there is just a cycle decomposition of the complement. And then if A has Möbius inversion, you can write the components of the inverse as 1 over the determinant. This we know how to expand combinatorially, and then the numerator is like a sum over these connections of the weight of the connection, where again the weight of the connection is the multiplication of all the weights of the arrows that appear in the corresponding paths and cycles. And then the sign of the connection, which is similar, is like the number of objects plus the number of cycles in the connection. So here you won't count the path, but then +1. Okay, we could imagine this +1 comes from the path. So yeah, I also want to introduce an example of that. So if you want to compute theta -1 of 1, 1, so the first component of this component of the inverse, then you do 1 over -2, so this is 1 over the determinant, we already computed. And then you have to multiply by all this sum over possible connections. But indeed, when you remove 1, no, because we said 1 in this case where A equals B, there is nothing around 1. So you remove 1. The only cycle for the complement is just the cycle made by the two loops, no? Because if you go from 2 to 3, then you can't go back. And this thing has weight 2, which is just the multiplication of the weights. And it has sign +1, because it's -1 times the number of, to the power, the number of objects, which is 3, and then the number of cycles, which is 2, +1. That's the sign, makes the sign +1. So this is what you get. So this means that, like, yeah, this is just -1, this component. And similarly here, if you have the inverse of theta, now the component 1, 3 of the inverse, this will be 1 over the determinant. And now there are two possible connections. So there is a connection that is made by this path. So this path already visits all the vertices. So there is nothing apart besides that. Okay, you're already visiting all the vertices. But you also have this other connection when you go directly from 1 to 3. And in this case, though 2 is in the complement of that path. So you need to introduce it in some cycle decomposition. And in this case, because 2 is all by itself, well, the only cycle possible is this self loop. This has weight 6, and this has weight 2. And well, and here I'm computing the signs, and yeah, that gives you an answer in this case. I would say this case is simple enough that the combinatorial method is indeed like maybe an efficient way of computing the inverse to some extent. Of course, in general, it's very involved. So I think that maybe more generally, it can be more of like a theoretical interest. Maybe that's what I want to touch in this perspective section. So, but before getting to that, I just wanted to mention that, okay, you can recover Leinster's theorem because, as I said, under all these hypotheses, the only cycles that you can have are self loops. So that the only linear of the graph is made only of these self loops. So that means that the determinant of zeta just has one term, it's a sum, which is one term. And this term is just the multiplication of all the zeta values set of the form zeta AA. And so that is going to be your denominator in the formula. And now for the numerator, you have to compute all the linear connections. But the linear connections are going to be, sorry, the connections, but the connections are going to be in one-to-one correspondence with paths. Now, because precisely every time you have a path, then there is only one cycle decomposition that you can make of the complement, which is just the cycle decomposition given by self loops. So in this, under this particular hypothesis, yeah, the description simplifies a lot, and you can compute the components of the inverse as a sum now over paths, because every path determines a unique connection of well, it's an alternating sum. Here you have the weight of the connection. Here you have the weight of the unique linears of the graph, which is the determinant. Now, this is a sum in DA. Now, it's not a sum in the category. It's a sum in this associated graph. So that indeed here, this is measuring like a multiplicity. So it's like how many different paths passing through these objects you could have in the category. So this represents the choice of arrow between C0 and C1. This is the choice of arrow between CK minus 1 and CK. So that when you transport this description to a description on the category, then is when you get Leinster formula. Here is a sum over paths on the category with the signs, and then this normalizing factors. Okay. So yeah, I mean, it's a very kind of brief explanation of how the proof works, but the thing that I want to illustrate is that you can recover this proposition in a kind of natural way. But the advantage now is that indeed we have a more general proposition that is valid beyond this hypothesis. And then in the application to metric spaces, what you're going to do when you start with a metric space, you're going to have a complete weighted graph, okay? Where like every edge between points x and y is going to have this weight, exponential of minus t, the distance from x to y. Now, you could also have a submatrix of this given by any sub-collection of points. I'm going to write those zeta x tilde t, okay? So we can extract submatrices if you want. Now, this is going to be useful just in one or two slides. Now, you can prove also, yeah, that, for example, the limit when t goes to infinity of the magnitude is the cardinality. And again, yeah, I mean, I won't even go through the proof, but it's basically, again, you prove that in the limit, the only connections that survive in a certain sense, taking the limiting procedure in terms of the weights all going to zero, except when you have a linear subgraph that is just made by self loops. Each one of the self loops has weight 1, so those don't go to 0. And also similarly for the connections. So you can recover this thing. But this is kind of well known, and this is what justifies seeing the magnitude as some kind of generalized cardinality. So yeah, I think this sign expression that we have now, yeah, I was hoping that can give a better perspective when it doesn't behave like cardinality. So precisely the magnitude can be negative, for example. So can we understand from this more fundamental perspective when the magnitude is negative, things of that sort. Okay. So yeah, we're still working on that. Now, I have like 3 minutes, so I just wanted to mention these perspectives. How many minutes do I have? Maybe 5. Maybe started a bit late, but
yeah, it's not that strict. You have as much, like 5 minutes or so.
yeah, I'll say 5. I wanted to present. Well, anyway, maybe before I said this, is there any remark or question about what I've said so far? No?
No, nothing.
Well, okay. So there is. What is magnitude homology? And I think this is very interesting. And maybe this is what can motivate someone here, because I think that I want to present 2 examples here. So this is my metric space. So if you want in R2, you take this collection of points on an integer lattice or something, where are at a distance like 1, 1, 1, 1. Everything is a distance 1. Now, if you have here, I will present 2 examples. One with connections, one with linear subdivisions. So consider these 2 connections. So you can have a connection which is given by a path from 1 to 3, and then this self loops. This connection has sign 1, okay? So it's, and has weight exponential of minus 2t, okay? Because, yeah, these things don't contribute to the weight. All these weights are 1. But here you have a path of length 2, so this is the 2 that appears here. Now, you can, because these 3 points are collinear, when you skip this point, the distance is still 2. So now, on this point, you can put a self-loop that doesn't contributes, changes the weight. The weight is still exponential of minus 2. But because you change the number of cycles, now there is one more cycle, the sign flips. So then now these 2 connections cancel in the sum over all connections. And if you know a bit of magnitude homology, you'll see immediately, okay, this has to have something to do with magnitude homology, because indeed, the boundary magnitude homology corresponds precisely to skipping a point, preserving the distance. So so the magnitude complex is made of paths in the category that have a fixed length, and you have a non-trivial boundary operation when you are able to remove a point from the path, keeping the length. So this is precisely what's happening here, because we're able to remove 2, keeping the length. So we could say that this thing going from 1 to 3 is the boundary of this path in magnitude homology. And because we're only putting a self-loop here, we're preserving the weight even when we go to this more general setting of connections. So here there should be something like magnitude homology behind. And then with the linear subdigraphs, is, well, not so similar to magnitude homology, but there should still be something. Because, for example, here, when you consider the full cycle, this has length 6. So there is just one, because there's just one cycle, well, you can compute the sign, it gives 1. And then because it has length 6, it's exponential of minus 60. Now, you can interchange the roles that this point and this point play. So, which means this arrow, instead of pointing here, now it's going to point here. And this arrow, instead of pointing here, now it's going to point down. And then you get this. And it turns out that this has the same weight because the length of the paths is preserved, but it has an opposing sign. So because you change the number of cycles by 1. Indeed, this operation is also natural, but now not in the context of magnitude homology, but in the context of this combinatorial linear algebra. Because this is what corresponds to flipping 2 columns of the matrix. So it's like here, like we flip the column 3 and 5, so that then the determinant is preserved, but all the linear connections get some kind of re-index by the fact that we flip these 2 components. Sorry, and the determinant changes sign by -1. No? So yeah, so there's something there. And another thing is that we have this kind of path integral formulation. I mean, that's a pretentious name, but I think in the limit should be something like that. So we can compute that the magnitude is a sum, now a finite sum, over all the possible finite paths. So here in the end, we're going to sum over all the possible finite paths, but paths that do not intersect themselves. So these are kind of self-avoiding paths. But the paths appear with a weight, and this weight is the determinant of the zeta matrix of the complement of the path, all the points that are not in the path, normalized by the determinant of the zeta matrix. So, and then the question is, what could happen if we take more and more points? Let's say you have an infinite metric space as a subspace of R2 or something, and then you take like an infinite sequence of points that converges to this space in the Gromov house of distance. Then what happens with this formula in the limit? So that is where maybe there could be something like a path integral, where instead of summing over finite paths, you would like to integrate over infinite paths. But I don't know how to do that. Maybe somebody knows. And the last slide is that this thing, that this can be generalized to pseudo inversion. So still it's not finished, but there is something here. And it's because the Kramer formula itself has like a generalization to the pseudo inversion. In the case of the pseudo inverse, indeed you can write the pseudo inverse as a convex combination of inverses. And for each one of those inverses, you can apply this Kramer formula. So this is called Dut's formula, this expansion of the pseudo inverse as a convex combination of invertible submatrices. And the idea is like by applying this combinatorial interpretation to each one of the invertible submatrices, then you get the general combinatorial interpretation. But now things get a bit messier because now a connection is it's not just given by one path, it's given by up to R minus one paths, like where up to R paths, where R is the rank of the matrix. So yeah, so there's still something to be done there. But I think that would give the general interpretation that I mentioned. So yeah, so that's the end of the presentation. I just presented a new definition of the magnitude in terms of the pseudo inverse, which poses the question of, okay, can we find a general interpretation for this formula as Rota did for his more simple theory? And at least we can do it for like the true inverse, and then we get this formula in terms of linear subgraphs and connections. And this in particular gives this new expression for the magnitude as a quotient over finite sums. And we saw that there are these cancellations that are like similar to those in magnitude homology. So there might be an homology theory behind that too, so that each of these sums can be re-expressed as an alternating sum of Petty numbers. Probably this can be generalized to, or at least part of this theory can be generalized to the pseudo inverse using that formula. So I will stop there. Thanks for your attention.
Thank you very much. And let's all please unmute ourselves so that we can clap together for our speaker.
Right, thank you.
And I'll open for questions. Does anyone have a question? Georg?
I see a hand.
I was just seeing Henry also leaning forward. I didn't want to cut you off, Henry. A very, very interesting talk. And there's a lot I don't understand. So I actually want to sort of tap into what you just said about is there a way to possibly connect this to, homology and Petty numbers? You had this slide where you interpreted the removal of a middle point of a line as a boundary. And I was wondering if you could talk me through what happens if you have one more arrow, if you had 3 points instead of 2 and you remove 2 points in the middle. Is that just an alternation of the sign happening, or am I missing something? I don't know if there was just a couple slides before.
No, yeah, that's what happens. And I think that's something that definitely you can maybe look, you can find in this article. There are a couple of articles that define magnitude homology for graphs initially and then for metric spaces. And yeah, they introduce this boundary operation where if you can remove a point preserving the length. And it turns out that, if you have, let's say you had 4 and you remove 2 in between, in any case, you're going to preserve the length, but there will be like a sign that flips so that indeed then when you do like d square, indeed it cancels, so it gives 0.
Yeah,
So
interesting.
so yeah, that's something. I mean, it's not my idea. It's something that is out there. So
Because the reason why I'm thinking about this is like if you really just think of that as a directed graph, and you think of an endpoint as a boundary, right? Something that would give you a very naive sort of simplicial homology. You would want to have enough information to get 2 boundaries there, right? If you remove 2 middle points. And given that you're just flipping the sign, it almost seems like you don't have enough bits to encode that you have, because like the case of removing nothing and removing 2 points looks the same, right? So I don't know. I'm sort of trying to get an intuition how you would get to
no, well,
yeah.
I mean, I don't know very well. This is very if you want, I hear him presenting just a motivating remark. It's like there is
no, I'm sorry, I don't want
I
to
don't
strive too far from what
really
you
I don't
presented.
really have a theory of this yet, let's say. But the motivating remark anyway is that okay, you can somehow pair these connections in a way that they cancel pairwise. And this way in which they can be paired, I mean, I'm not saying that every connection can be paired, maybe some of them cannot, but like some of these can be paired in this fashion. And this is like related, I think, in a kind of close way, precisely because we are using this fact of removing a point from a path, but while preserving the length. Is very connected to this combinatorial operation in magnitude homology. Now, how could this be exactly exploited to do like a systematic simplification of the subs? Yeah, that's what I would like to answer. And that's what I don't know very well, but I suspect that if something like that exists, now because, that is kind of the fact that there is like a chain complex like that, and then that when you go to this Hall's formula, you can interpret, so this was at the very beginning, but the fact that you can interpret each one of these things as a cardinality of a certain chain, like collection of chains, etc. So it's also like the basic building blocks to then do this identification with magnitude homology. So I think those ingredients are there, but like the theory is still a bit complicated.
Yeah, no, I think it's super interesting, and actually it smells to me that what you like in a way, like a path of a length is sort of not a very homological thing, right? We deformation retract things all the time. We do homotopies, and we just end up with cycles, right? That's in a way a very hand-wavy way to think about homology in the simplicial case, at least. And so they seem to be antithetical, right? And so maybe the answer is to combine what you're presenting, something that actually gives us a way to count path lengths with the homological information, and you need to enrich these 2 things to do it. But I think it's super interesting. I actually have so many questions, but I feel like I'm dominating the question section.
But the magnitude homology is already a very rich theory, and it has this very strict metric information that you can relax a bit sometimes. So instead of considering exactly length L, sometimes you can change the chains to be up to length L. But in any case, yeah, it's an homology that looks different from usual homology, and indeed encodes more geometric information than usual homology. This is not all invariant under like deformations as it could be usual homology.
Right.
And it's because all these chain complexes are defined for a fixed length. So you do it for each possible length. Then you have to integrate, if you want, over all the lengths. And then is where things get tricky, because you can only do it in a meaningful way when you can indeed control that this sum makes any sense. And so there is some technicalities, if you want, like behind that. But I think those technicalities are very well understood in many cases. In say metric space, certainly for graphs, whereas like I would say the case is the most developed.
All right, well, thank you so much. Yeah.
Thank you. And Henry?
Juan Pablo, I wanted to ask a question about your slide where you mentioned the Gromov-Hausdorff distance question.
Yeah. So yeah, this has to do with the fact that, okay, I said there are like 2 branches of work in magnitude. And one has to do with this magnitude homology. I mean, that's the biggest one nowadays. But on the big one has to do with analysis. Okay, so so it turns out that every metric space, we went very quickly over this, but every metric space is an enriched category. So that was the interest of introducing this word enriched to begin with. Is every metric space is an enriched category over whatever, over the positive real numbers. Which means that you can apply all these techniques. And introduce this magnitude of a metric space. Let's say finite metric space initially, okay? Because we did all this for finite category. We need matrix category. We do finite metric space. Now, but then the question is, okay, and this gives an isometric invariant of metric space. But then the question is, okay, but what happens with infinite metric spaces? Normally, we're interested in them. So in some cases, when you have what are called like metric spaces of negative type, which means that this theta function is a positive definite matrix, it's like a counterintuitive nomenclature. You can indeed define the magnitude of the infinite metric space as a limit of magnitudes of finite subspaces that converge to it in the Gromov-Hausdorff distance. So indeed, like there's an I mean, in general, I think there's just lower semi-continuity for the operation of like, if you just do it in general, but if I remember well, when you have this negative type hypothesis, then indeed there is convergence. So which would mean that we could take all these magnitude formulas for finite spaces that I'm presenting here, this kind of nasty sum, and try to compute, now take this finite space as a converging sequence towards an infinite one, let's say like the Euclidean ball, whatever, your favorite metric space, and try to see what happens in the limit. So in the limit, of course, the sum is not going to be a sum anymore, and this is what I'm calling, okay, maybe in the limit is something like a path integral. Somehow, how to understand that limit? And is there a way of, like a path wise way of understanding it? Now, the magnitude has a lot of rich connections with geometric invariants. So in particular, somehow the magnitude knows a lot about geometry when put together in this thing that's called the magnitude function. So here we are not really computing the magnitude only for the distance t, but we are allowing ourselves to scale the distance by t. No? Oh, something happened. To scale the distance by t. So that's when the weights we have a t2. So this gives a function of t. And this function of t knows a lot about the geometry of x in a very mysterious way. So in the limit, for example, when t goes to infinity, you can recover the volume of the metric space, you can recover the surface area, you can recover the Minkowski dimension, you can recover some other geometric invariants. And also, even when you don't go to t, go to infinity, so it's like, even locally, you have some, anything like, maybe there have been some presentations about that here, but there's like a local dimension. So there is a big interest in, so maybe, for example, if you had something like a path integral formulation of this general magnitude, you could also link it to stochastic processes, something like a Feynman-Kac formula, or something. Then you could get like a different view of how the geometry appears, or why the geometry appears. But okay, that's very far in the future. I don't have a theorem about that.
Thanks, I appreciate it.
Hey, any more questions? Okay, then maybe I will end the recording here. But first, let me thank you again. A great talk.
Thanks. Thanks for the invitation.